Continuing on with the Arizona Educator Proficiency Assessment preview, we are now doing number 4. It involves complex numbers. You can see I have them written down here. I changed them a little bit from what is actually in your study guide. I changed them because I'll work out an answer here, and you should be able to use the same methods to work out the one that's actually in your book. You have the answers for them in the back of your book. So I'm going to change the numbers ever so slightly. At the end, I'll tell you the relationship between this and that if you don't already see. But we're going to solve this one. We're going to multiply these two together to get the product Z1, Z2. We're going to write that answer in polar form. Ordinarily, when they tell me to write the answer for any question in a certain form, that's kind of the last thing I deal with usually, right? I'm usually all about just get the product, and then toward the end start saying what form do I want it in. There are times you want to kind of reverse that, but I see people worried about this from step 1 and they kind of stop themselves from doing the algebra. I'm just going to do this, and later on we'll worry about that. Technically in your course, going polar form would kind of force Euler's theorem upon us from the get-go, and they don't really cover Euler's theorem in this material very much. So we're just going to do this as your regular standard A plus BI standard form. We're going to write both of these down. They already are A plus BI. This one would technically have to be written as 1 minus rad 3I to be A plus BI, but good enough. We'll leave it alone. These are Cartesian form. These, by the way, for those that maybe don't remember, if we plotted the point AB, and on the x-axis we put our real coefficients, the A, and on the y-axis we put our imaginary coefficients, the B. This vector right here would represent A plus BI in Cartesian form, because the A, if I follow my SOHCAHTOA from trigonometry, this length here is A, so that'd be an x value of A. That length would be the B, so it would put us at A plus BI that way here. And those things do come into play with what we're doing when we multiply things out and when we square things and raise to powers. These two down here, Euler's theorems and de Moivre's theorems, you can look them up online if you wish. Those will go back to doing things of this nature and really make a lot of it a lot easier. But we're just going to multiply them out like that. So Z1 times Z2, Z1 is 1 minus I times rad 3. Z2 is negative 2I. And again, I changed them a little bit from what's in your book. We have this. If I multiply, if I'm doing an A plus BI times a C plus DI, I would FOIL. Technically, this isn't called foiling because there's not two terms, but we just have one term multiplied by two terms, and we do it the way we always would. We're just going to multiply the negative 2I by this and by that. Whatever we get is going to be our answer. So 1 times negative 2I is negative 2I. Negative times a negative makes it a positive. Rad 3 times 2, I'm going to pull the 2 out front and make it a 2 rad 3. The I times the I gives us an I squared. And that's something we don't want to leave as an I squared. In general terms, when you're doing i's raised to powers, you almost always want your answer to be either a positive or negative 1 or a positive or negative I. Right? So we don't like to leave an exponent on the I. It generally doesn't serve a whole lot of purpose for your final forms. So we're going to get rid of that I squared by recognizing what I is. By definition, I is the square root of negative 1. So if I take that I right there, if I raise both sides to the equal sign to the second power, if I square them both, this to the second power is I squared. That to the second power, the squared and the square root would cancel and just leave you with a negative 1. So this is negative 1. So if we do that, negative 2I plus 2 rad 3 multiplied by negative 1, that negative on this positive 2 makes it a negative 2, so I can just change this sign right here to a negative. Get rid of this, and it's condensed a little bit more. This is now our A in the A plus BI form. It's now the negative of 2 rad 3. The b is now this -2, so we're just turning it around so we can have the imaginary term. So you can have the imaginary term as the second one because that's the way it's always written with the a plus bi. It's equivalent to bi plus a, but Math World likes this better. So we're doing that one there. This here would be the product, but it's not in polar form. And that's where these things kind of come into play with the graphing over here. If I'm doing this, this is actually in the third quadrant because I'm going, real axis is your x-axis. Our real part is a negative, so we'd be going to the left. Our imaginary part is also a negative, so we'd be going down. So I want to redraw this graph and put it down here. So I'm going to go ahead and erase that up here, redraw my graph, showing more of the quadrant 3, because this is probably the best way to go about putting this into polar form. I could just give you formulas, but whether it actually makes sense. 2 rad 3 is roughly 3.4, it's close enough. 3.4 and 2, so we're like 70% longer on the real part. So I'm going to go ahead and put down a -1, -2, -3, and kind of locate it roughly where it would be. Real part -2, if I repeat the process down here. Now the hard part, straight lines on a dry erase marker board, not the easiest thing. That there, in terms of a plus bi type stuff, this would be the point, -2 rad 3, comma, -2. That's where that big point right there is. So I mentioned vectors and add a vector on it. If I went from the origin to that point, we would get this arrow. I'm probably going to miss it. Not close enough. Just made it worse. But if I had that arrow there, that arrow would take us right there. And you can kind of see if I did that, it would form this right triangle. And that right triangle we have, that's what we're going to use to rewrite this arrow in polar form. Polar form is when you go from x, y, which is where we're starting off. Polar form really isn't the x, y. It's rewriting it as r comma theta. It's one of those kind of somewhat weird things where pretty much every time they give you an ordered pair, it's generally speaking input, output. This stuff, you pretty much always do r equals f of theta if you're writing formulas, which means your input is the theta, which is the second one here. So they kind of swap the input-output thing. But that's polar form. We want the radius, which is the length of that. And we want the angle theta, which is going to be measured in your standard trig form, which means we're going to start with 0 degrees being here, the positive x-axis. It's going to increase as we wrap around, so the positive y-axis is 90 degrees, 180 degrees, and a little bit extra. We need to find that extra part here, because we're doing 0, 90, 180, and then the extra. So I'm going to call this theta, sort of theta prime, because we really need to give them the answer measured from the positive x-axis. In terms of solving our triangle, we're going to think about that there, theta prime. It's actually a reference angle, so I'm going to put a little subscripted r with it for reference. It's a reference angle. So anyway, we want the r theta. Get rid of some of this extra stuff here. Pull out a different color. Might as well go for purple. I have it up here. We want that, the r comma theta. So we need to figure out the r. Well, if we look at this, we have a length of the right triangle, length being 2 rad 3. That is, one of our sides of the right triangle. We have this side over here is 2 units long. I just dropped my negatives. I'm just getting the length. If we now do the a squared plus b squared equals c squared from the Pythagorean theorem, the c here is the length of the hypotenuse. That's what we want. So I'm going to call that an r squared. We need to get rid of the squared, so we would square root both sides of the equal sign. we're doing this as strictly a positive value, so I don't do a plus or minus on it. These A's and B's are the same things as these A's and B's up here. Technically, I could swap the order, but might as well keep them the way they are. The A is the 2 rad 3. So if I did this, do not let yourself write it this way. That is incorrect. This would only be squaring the square root. The B is the 2. We figure this out. The square goes with both the 2 and with the rad 3. 2 squared is 4, rad 3 squared is 3. This is 4 times 3, which is 12. That's 4, so this is 16. So we get the square root of 16 equals R. We're just going to say that's 4 because it is. Right? I'm going to erase this stuff over here. Euler's and de Moivre's again. Do a Google search. Fairly simple little formulas. You don't need to understand the derivation. If you want to, go through them. But they kind of do this stuff for you pretty easily. Anyway, we have this, R equals 4. That's the length of this arrow right here. Right? We want to get the angle up here. So I'm going to use green because I have not used it yet. I'm going to write out so ka toa. Probably most of you have seen this. The sine of theta, the sine of our angle, not that theta, just any theta. Sine of theta equals the opposite over the hypotenuse. The cosine equals the adjacent over the hypotenuse. The tangent equals the opposite over the adjacent. If I'm looking for this right here, I could use this and set up a relationship. I know all of my sides at this stage, because this is 4. So I could pick any one of those I wanted to, and I could go through that. But you kind of, in these courses, I recommend in general to students when they're doing a multiple choice test, always glance at your multiple choice answers. We don't have any weird decimal type answers on these. Kind of makes me think we might have some special angles involved. And if we have special angles, I kind of want to think about 2 special triangles, which you've seen before, but they might not be really fresh in your head. The first one I'm going to do is going to be the one that we don't need for this one. Horrible right angle. I am not doing these on a unit circle. These are the ratio of the sides of a 45, 45, 90 right triangle. 1s and rad 2s and stuff. What we really have for our ratios, you'll notice our short side is 2, our hypotenuse is 4. Hypotenuse is exactly twice as long as the short side. That one actually happens in the 30, 60, 90. I'm not putting my little degree circles here, forgive me for that. Dry erase markers are kind of fat, kind of hard to write all those things. But I get that 1 to 2 ratio right here between this side, or short side, short leg, and the hypotenuse. Hypotenuse is twice as long as the short leg in a 30, 60, 90 right triangle. We have that. Short leg is 2, hypotenuse is 4. That's a 2 to 1 ratio, as are these, right? So notice I'm looking for the one that's opposite the short side. Opposite the short side is this 30 degrees. That is what we have up here. And that is just our reference angle. If we have a reference angle of 30 degrees, we have to get the standard trig angle, which is measured from here. So we're going to have 0 degrees, 90 degrees, 180 degrees, and 30 more. I'm kind of blocking that. 0 is that way, 90 is that way, 180 is that way, 30 more is 210. So our theta should be 210 degrees. So for this stuff, we get R equals 4, theta equals 210 degrees. Though I changed our numbers, what I actually did, I took the ones in your book, I multiplied those by a -1, each of them. So I took the one from your book and said that times -1 is this one. Their Z2 is times -1 gives us this one. If I multiply both of these by -1, -1 times -1 is +1, so it's just going to be the same product. So I did this, I changed the numbers a little bit just to work out a different one because I want you to work this out. But we should get the same answer, that, which I believe was answer D. Yep, answer D. So that was number 4.